Hello, this is the video presentation for the obstacle detection and avoidance system for an unmanned aerial system using a LiDAR. My name is Andrew Moffett, and I am the team lead for 4 aerospace, computer science, and high school students working on this project. To overview this presentation, first I will discuss the project's background, such as objectives, applications, and used hardware. Then I will describe how we approached the problem and the logic behind the avoidance algorithms we chose and tested. Finally, I will talk about our test results and potential future work for the project. To start with, we defined our main objective as developing a 2-dimensional obstacle avoidance algorithm with the longer-term goal of making it 3-dimensional. For applications, a collision avoidance algorithm offers a wide variety of potential uses. We saw the main uses being for commercial package delivery in urban areas, traffic monitoring, power line inspection, and potentially hazardous humanitarian missions. The UAV we used for this mission was the DJI S1000 multicopter. It offers a large carry capacity for onboard processing and resilient LiDAR mount protection. The flight controller we used was a PixHawk2, which took commands from the onboard computer, an Intel NUC Plus. It processed all information coming from the most important piece, our LiDAR, the VLP-16. With this added weight, our flight time was reduced from 15 minutes to around 10, but it was still plenty of time to complete our mission. Here is a further breakdown of the vital components used to operate the UAV. Connected to the PixHawk is a receiver FrSky L9R that communicates with the Taranis XD90, giving us safe manual control at longer ranges. The drone's location is kept track of by the 3DR GPS, and this information is all reported back to the ground station through the FPV telemetry module. For UAV control, the PixHawk2 uses ArduPilot, an open-source drone autopilot software. This software is a powerful tool for the team as it is the foundation of our avoidance algorithm. The algorithm itself is calculated using the onboard computer, an Intel NUC Plus. Its operating system is Linux Mint and can run DroneKit scripts, which we use to give the autopilot commands. The LiDAR we use is also very interesting. Unlike most one-dimensional distance-finding LiDARs, the Velodyne VLP-16 uses 16 vertically stacked lasers to send out pulses of light. It then can generate distance values from the time it takes the light to get back, similar to sonar. Rotating these lasers around at 600 RPM and taking distance values every 55 microseconds then can give you a point cloud. The lower image is an example of a point cloud generated in the Cal Poly Pomona work lab. This particular image was captured using the prepackaged software VeloView, which saves data as polar and Cartesian relative to the LiDAR. Unfortunately, the pre-made VeloView software could not meet our need, and we ended up grabbing LiDAR points manually through a UDP port on the Intel NUC. The image to the left shows how raw data is sorted by the LiDAR. Each scan is a block with the angle and distance values of all 16 laser channels. We decoded the information from its raw hexadecimal to a useful polar coordinate points using a custom script. Then, as seen in the image to the right, once the data is received and the Intel NUC decodes and parses the information, it is sent to the obstacle avoidance algorithm as useful data. Getting the data this way, while more difficult, heavily increased response time and the volume of data that could be sent. Our technical approach for tackling the challenges of autonomous obstacle avoidance was as follows. We began by simultaneously preparing the UAV hardware and researching previous work on the topic. As we developed the algorithm from this research, we began integration of the flight controller, LiDAR, and onboard computer. We then wrote a script using the Python library DroneKit to take commands from the algorithm and output UAV movement commands. We would then test these commands for validity in simulation and flight testing. We developed and tested 2 different avoidance algorithms. The first algorithm calculated its heading by modifying the original trajectory by an angle inverse the distance. So as an obstacle got closer, the more the heading angle would change to avoid it. This method was simple and could be applied to an unlimited amount of objects from any direction. It, however, had issues handling the large amounts of points generated from the LiDAR. The algorithm was tested on the ground to verify the validity of its outputted heading. The UAV was placed with its end target being on the opposite end of a tree. The LiDAR was turned on, but the motor power was disconnected. We manually read the direction the drone wanted to fly in and incrementally moved it accordingly, as seen in the upper pictures. To our excitement, the algorithm successfully pathed around the obstacle, and minor iterations were made on the sensitivity of the algorithm's equation. Unfortunately, at a subsequent flight test, an issue unrelated to the algorithm itself caused the drone to crash, putting the team back some. However, even without flight test confirmation, there were some glaring issues with the limitations of the algorithm, which we addressed in our next attempt. The second avoidance algorithm, and the one that we ended up moving forward with, uses edge pathing logic. As seen in the flowchart, The LiDAR data is merged into a connected wall of points with a safety margin. If the straight line path is blocked, it will test each heading around the edge and pick the shortest distance. It then checks if it has reached its end, and if not, recalculates the heading again. The visual in the top right shows the logic of the drone if confronted by a wall. To test the algorithm, a Java GUI was created using Abstract Window Toolkit. It can visually show what the algorithm will output given different points. Unlike the first algorithm, which could be easily debugged because of its simplicity, this GUI was instrumental in testing and iterating on the edge pathing algorithm. As seen in the figures to the left, walls were constructed out of messy point clouds. Then the heading or path line would be calculated to point around any edges. This was recalculated as quickly as possible, as LiDAR data would refresh much faster than the algorithm could output a new heading. With these tests and the new limitations on flight testing, we felt confident to begin constructing our concept of operations for simulation testing. To demonstrate the algorithm under as close to flight conditions as possible while being unable to actually fly, we devised a concept of operation for simulating a flight test. Using DroneKit's SITL, we were able to create a simulated drone entity that we could connect to the algorithm script and ground control station as if it was a real independent UAV. We then simulated LiDAR data by returning the location of obstacle points as seen in Figure 4 relative to the UAV. The mission was performed in simulation and monitored using the ground station software called Mission Planner, where we could save and analyze results. The trickiest part of the simulation was creating fake LiDAR points while still using the framework that we had built for flight testing before. As seen in the figure, we had the DroneKit script grab position data of the UAV in the simulation, where it then calculated the distance it was from each obstacle point. This was then handed back to the drone through UDP as if it were real LiDAR data points, leaving the rest of the process independent. The results were a success, simulating an obstacle 30 feet in front of the UAV with the end goal on the opposite side. The simulated drone was able to navigate around it to its final destination. The path that the UAV took is the purple line, which was captured by Mission Planner reading directly from the telemetry of the UAV. The simulation was in real time and the data was captured in log files just like real flight tests. These flight logs were then plugged into MATLAB and the data plotted as seen to the left. Depicted is the heading versus time of the UAV during the same simulated mission from the previous slide. As expected, the algorithm incrementally shifted the UAV's heading after each recalculation before passing the obstacle and returning the heading to the final destination. DroneKit SITL, the simulation software, also creates noise or disturbances in the telemetry, just like a real drone's flight test, making it more realistic, but also giving the algorithm more to do and adding noise to the data itself. While these results were exciting, we still believe there is much more work to be done. The biggest item for continuing would be increasing the test cases of the algorithm in simulation. The biggest hurdle with that would be improving the algorithm for simulating LiDAR points. Outside of simulation, we still strive for our long-term goal of a proper three-dimensional avoidance algorithm. This would most likely require a major revamp of the current algorithm, however we feel confident that it can be done. Additionally, performing and setting up physical flight test demonstrations is a major goal for us, as we'd love to obtain video of the working algorithm and be able to work on addressing weight concerns and other flight considerations. In conclusion, our team parsed data points from a VLP-16 LiDAR to detect nearby hazards. We then created two different avoidance algorithms that could navigate and successfully avoid collisions. In order to address the flight restrictions, we created simulations of the drone and LiDAR data and tested our algorithms successfully in that environment. These results are promising, but we have a lot of room for improvement in test cases and functionality going into the future. To wrap things up, I would like to thank our mentor, Dr. Bhandari, for supporting and guiding our project. I would also like to thank Lockheed Martin and the National Science Foundation for their generous funding and project feedback. Thank you.